Understanding of what's being asked for. So in this case, we've got basically a ball sitting in a tube. The tube is 1 meter long, and there's some method that the tube has, probably compressed air, to supply some force to our ball, to project it upwards. And the question gives you what that force is, a value for that force. And then it asks, well, how high does the ball go above the end of the tube? So we've got a 1 meter long tube. The air exerts a force of 2 newtons. And the question is, well, how high does the ball go above the top of the tube after it's been fired? So this is into chapter number 37. If you haven't had a chance to get it down in your notes, or get the full problem down in your notes, that's where you need to look for this statement. So I just want to write down the key information here. Mass is 50 grams. The tube is 1 meter long. What I'll call my thrust force is 2 newtons. And then I want to know max height of ball. Okay, and before I even start writing down pictures here, can anybody offer a pathway through this problem? Anybody? Can anybody see it right at this moment? How we would go about solving this thing? Okay. Okay. I didn't hear the last. Okay, kinematics after that. Okay. You're definitely going in the right direction, and probably are completely right. Although,
velocity equals 0, and then find the time.
Okay.
And then plug the time into an equation to give you delta y.
Okay, we could probably go that way. So what I'm digging for actually is that there's two different parts here, and we're going to see that as soon as I draw out this motion diagram. There's a part when the ball is inside the tube, and there's a part as soon as the ball leaves the tube. And the forces acting on the ball during those two different parts are different. So I've got my x and y direction here. Put some tube with my ball at the bottom of it. And I'm going to label this with y naught and v naught. And then one more point of interest is when my ball leaves the tube, I can label this with y1 and v1. And then my final point of interest is when my ball gets to its maximum height, somewhere up here. Y2 and V2. And to be perfectly complete, I probably should put subscripts on the velocities, but we don't actually get them in the problem. So this is kind of what I was digging for a minute ago. My strategy here is I'm going to break this thing into 2 parts. And part 1 is when the ball is in the tube. Part 2 is when the ball is outside the tube, or above the tube, however you want to put it. Let's see, let me go ahead and write down my principles. This is Newton's second law. kinematics, and my principle of superposition in this chart. Yeah. So, now that I've gotten that all taken care of, what's next? After writing out my motion diagram. Go ahead then.
Free body.
Yeah. Yeah, free body diagram, yeah. So I said I want to break this down into two different parts. So first off, I'm going to look at it inside the tube and draw out my free body diagram. So I've got my dot there representing my ball. What should I attach to it?
Gravity coming down, center of the earth.
So my contact force here is my thrust. So first do the contact forces, and then write in gravity. So let's see, I'm going to say this is F sub T for force of thrust. And then, what's that?
Can we just say that normal force, it's not touching the tube? Can we just say the ball is not touching the tube? Can we just...
Oh yeah, we need to. You're talking about from the sides.
Yeah.
Yeah. So that's actually.
That's manageable.
Yeah, that's an assumption that we certainly have to make in order to solve this problem, because we're not given any information about the friction on the ball on the sides of the tube. So this is a gross approximation.
Gotcha.
Here is what it is, but we'll work with what we're given. Okay. So we've got our force due to thrust. What should I write down? How should I draw my force due to gravity?
Straight down.
Okay, and magnitude? Shorter, right. So this thing is going to be projected upwards. So my gravitational force has got to have a smaller magnitude than my thrust force. Okay, let's go ahead and write down our knowns. Y naught equals 0. Y1, we said the tube was 1 meter long. Our initial velocity is 0. Our mass here is 0.05 kilograms. I need to stress that one. When we're working through these problems, we've got to use kilograms instead of grams. Always convert to kilograms. That's our SI unit. So we need to convert to kilograms as we go through these problems. There's one other piece of information that I can write down, and Austin, you said it a minute ago about the
Velocity line.
yeah. My final velocity is 0. Yeah. So my velocity when this thing gets to the top of the path is 0. So my velocity at the top is 0. Reaches a turning point. And let's see here. We need to find, here it said the height above the tube.
Yeah. Wouldn't velocity 2 be more in the outside tube part of the equation?
Yeah. I'm just writing down knowns and unknowns for the whole equation, for the whole problem. Yeah. We need to find here y2 minus y1. This is the height above the tube. Height above the top of the tube. Okay, so returning to my free body diagram here. I can say that the sum of my forces in my y direction is equal to my mass times my acceleration in my y direction, or my thrust force plus my gravitational force is equal to m-ay. My thrust force, my gravitational force in the y direction is minus mg equals m-a sub y. I can say then that a sub y, just by solving this equation, is my thrust force minus mg divided by m. I can go ahead and fill in numbers. My thrust force is 2 newtons. My ball is 0.05 kilograms. Gravity is 9.8 meters per second squared. And this thing is 0.05 kilograms. And by doing the math here, I get that my acceleration is 30.2 meters per second squared. that's great. Now what? Find V1, yeah, who said that? Thank you. So my acceleration here is 30.2 meters per second squared. Let's take a look back at this diagram. Ball here, ball here, ball here. We know that this now is 30.2 meters per second squared. We know that our acceleration on the second part, from when the moment when it leaves the tube to the moment when it turns around, is just due to gravity. It's g. We know V naught, we know V2 here. V2 is equal to 0. And we know this distance. This distance here is, no, we don't know this distance. That's what we want to solve for. So this distance here is our delta y. We think about this second part, and we think about the equations that are given to us from kinematics. One of them leaps to mind here. V2 squared equals V1 squared plus 2 AY delta y. When we look at this thing, well, we know that V2 is equal to 0. We know that our acceleration in y, when we're dealing with the ball outside the tube, is just due to gravity. It's g. So our only unknown, we've got two unknowns here. We've got V1 and we've got delta y. So we can take our acceleration that we solved for in the first part and find our velocity in the our velocity V1. So let's look at that particular piece. This is V1 squared equals V naught squared plus 2A delta y. So this is my first part. Taking a look at this ball starts from rest. So this is 0. We've got V1 squared equals 2. My acceleration in y inside the tube is 30.2 meters per second squared. My height of my tube here. My height of my tube is 1 meter. This is going to give me V1 squared equals 60.4 meters per second squared. Well, now that I know that, I can take this and go ahead and fill this in over here. V2 is 0. 0 equals V1 squared plus 2 AY delta y, or 0 equals V1 squared minus 2G delta y. If I solve for delta y, I get delta y is equal to V1 squared over 2G. I can fill in now my V1 squared is 60.4 meters per second squared. My value of gravity is 9.8 meters per second squared. If I fill in those numbers, delta y is equal to 60.4 meters per second squared over 2 times 9.8 meters per second squared. I end up with my height is 3.08 meters above 2. So, strategy here is to break the motion down into two parts. We look at the first part. The first part has one constant acceleration. The second part has another constant acceleration that's due to gravity. We use our information from the first part to solve for our starting initial condition here, V1, for our second part. and then we can gain the rest of the information from our kinematics equations. Questions? Everybody's still waiting. All right. There's an example problem in your text that's similar to this one, I think, with a rocket, toy rocket, shooting up. So it's one more to take a look at, and I certainly encourage you to look at all the example problems in the textbook. So talk about something a little different now. So those are your first examples of applying Newton's second law, which is basically what this chapter is all about. I need to return to the topic of mass. So when we talk about mass, we're talking about the amount of matter in an object. And mass is an intrinsic property of an object. Okay? It tells us something about the object, regardless of where the object is, what it's doing, whatever forces may be acting on it, etc. So we're going to draw some distinctions here in between mass and weight. Gravity. Yeah, we've dealt with this idea a few times already. Gravity is a long-range force between any two objects that have mass. Okay. So specifically, if we look at Newton's law of gravity, which we'll get to in depth, I think maybe in chapter 12 or chapter 13, assuming everything goes okay, we see that the force between two objects is equal to some gravitational constant times the mass of the first object times the mass of the second object divided by the separation between our two bodies squared. So this is our gravitational force. This is where our gravitational force comes from. This is a mathematical representation of our gravitational force. Now, of course, we don't use this when we're talking about just bodies on the Earth, or bodies near the Earth's surface anyway, within about 10 kilometers. In that case, we can make the simplification that our gravitational force is just equal to mg, and it's always pointing straight downwards towards the center of Earth. So in this case, our small g here is given by values from our previous equation. Our gravitational constant times the mass of the Earth divided by the Earth's radius squared. So g is equal to gravitational constant times mass of Earth divided by Earth's radius squared. And we could certainly use this on Jupiter, for instance, if we wanted to. Just mass of Jupiter divided by radius of Jupiter squared. To give us a new value for small g on Jupiter, for instance, or the moon, or whatever you want. But we know that g on Earth is 9.8 meters per second squared. So now that we've talked about mass, we've talked about gravity, we can talk about the concept of weight. And this is where you guys who have had this class before at some point in high school, what have you, may get confused because the textbook author uses a different definition of weight than some you might have seen in the past. So I encourage you to follow along with what's being said. Okay, so the textbook author is going to define the weight of an object is defined by reading a spring force from a calibrated spring on which the object is stationary. So in other words, I'm standing still on a scale, my weight is given by the reading on that scale, the reading on a spring scale. And also because here my spring force is a force, weight is measured in newtons. All this is going to be familiar for this slide, and it's going to take a drastic turn on the next slide. So if my scale is at rest relative to the Earth, so my scale is not going anywhere, it's just sitting in place. It's not being accelerated upwards or accelerated downwards. then my weight, we can say, that I read from my spring force is just equal to my gravitational force. This is equal to mass times gravity. And this is the common thing that we typically see in physics, is that the gravitational force is equal to mass times gravity, or the weight is equal to mass times gravity. And then so we make the point that when we're talking about the weight of a stationary object, the weight is mass times gravity. We start to get into a little bit of trouble when we start talking about the mass of the weight of a non-stationary object, which I guess we'll get to it on, soon, very soon. So, as we're talking about weight, there's a common misconception that probably 95% of y'all have, that I certainly had at one point, that there's some equivalency between pounds and kilograms. Well, it's a false equivalency. A pound is actually a unit of force. It's not a unit of mass. Okay? So, I've got the next line here is that the equivalency that 1 kilogram is 2.2 pounds is not a good conversion. And, that statement is only partially true when we're talking about being on the Earth. And the way it should actually read is that a mass of 1 kilogram, or an amount of matter that has a mass of 1 kilogram, weighs 2.2 pounds. So this is a unit of mass, this is a unit of force. So rather than having this conversion that says 1 kilogram is equal to 2.2 pounds, the actual correct conversion, because of the fact that pound is a unit of force, should be 1 pound is equal to 4.45 newtons. Again, we can get away with 1 pound, or 1 kilogram equals 2.2 pounds on the Earth because, well, G is constant. So we can get away with that and use that conversion. But it's not actually valid. Your textbook provides this simple example of this idea, talking about mass and weight on Jupiter. So in this instance, the free fall acceleration of gravity on Jupiter has value 25.9 meters per second squared. And it's asking, what is the kilograms to pounds conversion factor? So if we look at weight on Jupiter, this is just mass times our gravitational constant on Jupiter. And we're looking for a conversion factor. So we can fill in 1 kilogram as our mass. And then 25.9 meters per second squared. I see that the parentheses is in the wrong place there, and probably is in the wrong place in your textbook. But I think we can figure that out. This is equal to 25.9 newtons. And then we said that, well, 1 pound, remember on the previous slide, is equal to 4.45 newtons. So in this case, the weight on Jupiter is 5.82 pounds. So in other words, on Jupiter, 1 kilogram is 5.82 pounds. On Earth, 1 kilogram is 2.2 pounds. On Jupiter, 1 kilogram is 5.82 pounds. So this is a little bit different idea than anything you possibly might have seen before. And the key here is just basically remembering this conversion factor. 1 pound is 4.45 newtons. So, now that we've gone through that, we can go back and talk some more about weight. So specifically, your textbook defines weight as a measurement you would read while standing on a scale. This is similar to the feeling we have of how weighty we are when we're on an elevator, say, or on a fair ride on a roller coaster. So when you're on an elevator and you're going down and you're coming to a stop, everybody knows your body feels heavier as you're coming to a stop. Well, your weight, according to the textbook standard, is different in that instant of time. Your weight is defined as the quantity that a scale would read. So for instance here, I have a spring scale, and this is not extremely easy to do, but hopefully I can make my point. There we go. I've got a spring scale. This mass here weighs 1 kilogram. So if I start dropping it down and get to the bottom, okay, let me try this one more time. Drop it down, get to the bottom. Let's try accelerating it upwards. How about that? When I accelerate it upwards, we see that the scale flips this way. Okay, it reads as heavier. Now, we've all stood in an elevator at the ground floor, felt the elevator start moving. As soon as the elevator starts moving, we feel heavier, or our body feels heavier. That's the basic conception that the author uses in this textbook. So, weight is the force that a spring would have to keep your body from passing through the elevator floor, basically. When an elevator is accelerating downward, we feel lighter. And according to the textbook definition, then, because of the fact that we feel lighter, we actually weigh less in this situation. And although I will try to possibly further elucidate this by doing some math.